All right, folks, happy Thursday. We are going to be taking a look at 7.2 today. I know that we didn't get to it yesterday, but that's okay. I think we'll still be on track to have everything be on time. So just wanted to remind you folks that you have your exam number 3 on Tuesday. It's going to cover chapter 7. So all of the stuff that we've been, Friday Eve, I love that. So the test will cover all of chapter 7 and using some of, like, we're using a lot of chapter 6 in it. So it's not necessarily that it's covering chapter 6, but we're just using a lot of those, that information in chapter 7, okay? So let's go ahead and get started. So I've got chapter 7, section 7.2. So I'm going to share my screen and we can go ahead and get started with that. All right. So let's get started. 7.2 in your textbook covers co-function identities, which we talked about yesterday, but it also covers double angles and half angle formulas, or sometimes they're called double and half angle identities, okay? So let's get started. So we're going to take some of the stuff that we learned yesterday and help ourselves understand where some of these formulas came from, okay? I think it can be really intimidating when we look at a whole bunch of formulas and we're like, where did this even come from? And so yes, it's important to know the formulas, but I think sometimes by exploring where they came from a little bit, it might ease that anxiety of like, oh, I have too much stuff to learn, okay? So we're going to start off with our sine function. And we're going to start off with the sine, sum, and difference formula from yesterday. So that formula from yesterday was sine of u plus v. And when we had sine of u plus v, that was not equal to sine u plus sine v. Like, we cannot distribute it like that. But instead, we had to put it into the following formula. Sine u cosine v plus cosine u sine v. Now, what's different today is when we talk about a double angle, what we really mean is that the first angle that we're adding is actually exactly the same as the second angle, meaning u equals v. And so the double angle formula is actually a special case where we have u plus u, or we could say v plus v. But either way, if we plug this into the formula, we're going to end up with sine u cosine u plus cosine u sine u. Okay. And we, instead of writing sine of u plus u, we write that as sine of 2u. That's where that double angle name comes from. It's twice of a given angle, or double of that given angle. Now, if I take a look at this, sine u cosine u, is that equivalent or not equivalent to cosine u sine u?
It is equivalent?
Exactly, it is equivalent. So that means we don't have one of them. We actually have two sine u cosine u on that right-hand side, okay? So this is our double angle formula for sine, and it comes from the sum formula for sine, okay? So sine 2u equals 2 sine u cosine u. This is something that you definitely see in Calc 2 For sure, for sure. And then maybe in Calc 1, depending on your professor. Okay, so we're gonna figure out where the cosine double angle formula comes from using the same kind of reasoning. So yesterday we learned that cosine of u plus v is cosine u cosine v minus sine u sine v. And so today we're looking at a special case where u is equivalent to v. And therefore we can say cosine of u plus u equals cosine u minus sine u sine u. And what we can say is cosine of 2u equals, another way of saying cosine u is cosine squared. And another way of saying sine u is minus sine squared u. Okay. So this is the double angle formula for cosine. Now, some of you might be looking at this saying, well, gosh, this kind of looks like the Pythagorean identity, right? The Pythagorean identity we said was cosine squared plus sine squared. And what did that equal?
1.
It equaled 1, good. So here's what we're gonna do. We're actually going to take the Pythagorean identity and we're gonna use it to generate two other common forms of the cosine double angle identity, okay? Now, as we go through some of these proofs, sometimes we're gonna need the one we already have written, and sometimes it'll be better if we have one of the other versions that we're about to write. So one of the things I can say is everywhere I see a cosine squared, I can replace it with 1 minus sine squared. So that will give me 1 minus sine squared minus sine squared, which gives me 1 minus 2 sine squared u. And that is another version of the cosine double angle identity. To find the third version, we can go back to our original and go back to our Pythagorean, but instead of saying cosine squared equals something, we could say that sine squared equals 1 minus cosine squared and plug that in. So we get cosine squared u minus, instead of sine squared, I'm going to write 1 minus cosine squared u. And that's going to simplify to 2 cosine squared u minus 1. And that is the third version of the cosine double angle identity. Okay? So sometimes you're going to need the first one, sometimes you'll need the second one, and sometimes the third one will actually be the most useful. And so that'll be decisions that we talk about as we get to those different types of problems. All right, we've got one last double angle formula, and that is the tangent one. And so yesterday we mentioned that if we had tangent of an angle plus another angle, that we could write that as sine of the first angle divided by cosine of the sum, right? Sine over cosine could still work here. And so we're going to take that same approach for the double angle. We can say that this is sine 2u over cosine 2u. And on the top, we can write the 2 sine u cosine u. And on the bottom, we just need to choose one of the three forms for the cosine double angle identity. Okay, so that is one variation that you could do. You could just say, hey, I know sine, I know cosine, so I'm just going to put the sine over the cosine. It's going to give me the tangent. But what was the other form of the tangent sum formula yesterday? Anybody remember?
Tan U plus tan B over 1 minus tan U tan B.
Good, thank you. Okay, so let's take this second version and see what happens if we plug in U everywhere we see a V. That would give us tan U plus tan U over 1 minus tan U tan U. And another way we could write that if we wanted to simplify it is 2 tan U over 1 minus tangent squared U. Okay? So when it comes to tangents, sometimes this top one will be more useful. Sometimes the bottom one will be more useful, but you need to choose which one you want to use. Okay? And again, as we go through the problems, I'll try and explain sort of my reasoning when I use which one. That doesn't mean it's going to be the same reasoning that you use, but I think sometimes if we don't know how to make that decision, it's nice to hear what other people have to say. Okay? All right, so in summary, here are the double angle formulas. I think these would be a good idea to get on your cheat sheet for Tuesday's test, because again, we have so many different identities. We want to make sure we know all of them so that when it comes to proving identities or answering different questions, we know exactly which formula we're going to use. Okay, so that being said, let's jump into some examples. So example number 1, if sine alpha equals 4 over 5 and alpha is an acute angle, find the exact values of sine 2 alpha, cosine 2 alpha, and tangent 2 alpha. So what does it mean for an angle to be acute?
Less than 90 degrees?
Yeah, it's going to be between 0 and 90 degrees. Okay. Well, if I double that angle to get 2 alpha, how big does 2 alpha have to be? Like, what does 2 alpha have to be between?
Zero and 180?
0 and 180. Okay, how did you get that? Do you mind explaining your reasoning? You're right.
Since alpha is bigger than 0 but less than 90, I think the double of 90, in this case, that will be 180, and the 0 will remain the same.
Yeah, exactly. If you double the 0, you're still going to get 0. But if you double the 90, you're going to get 180, right? So my double angle is somewhere between 0 and 180. Now, I like to do a lot of pre-thinking before I go into a problem so that at the end, I avoid some of the really common mistakes. So while we're here, let's talk about the trig functions in their quadrants. Okay, so in the first quadrant, is sine positive or negative?
All are positive.
They're all positive. Good, because if you think about the x values and the y values, the x and y values are all positive in quadrant number 1. What about sine in the second quadrant, positive or negative?
Positive.
It's positive. Good, because sine is the y value and it's above the x-axis, so it's still going to be positive. What about cosine?
Negative.
Negative, because we've got a negative x value. Good. And what happens when we take a positive and we divide it by a negative?
Negative.
Good. So our tangent is going to be negative. Okay. So I like to sort of set this up. I know that at the end, I'm going to need to decide if my angles, my double angle values are positive or negative. Okay. So I'm going to start by drawing a triangle that represents sine alpha equals 4/5. Okay, so here's my alpha. That means that I can label the opposite side 4 and my hypotenuse 5. How long is the missing side?
3.
3, good. So the 3, 4, 5 triangle, pretty common one, okay? But if you didn't remember that, you could always use your Pythagorean identity to find the missing side, okay? So once we've drawn our triangle, now we can find our sine 2 alpha, cosine 2 alpha, and tangent 2 alpha. So sine 2 alpha, that formula says that it's going to be 2 sine alpha cosine alpha. And everywhere I see sine, I can put 4/5. And what do I put where I see cosine?
3/5.
3/5, good, because it's the adjacent over the hypotenuse. And then you just multiply all the tops, multiply all the bottoms. So we will get 24 on the top and 25 on the bottom. And that is what sine 2 alpha equals. And it should be positive because according to our chart, we knew that sine was going to be positive no matter what. Cosine 2 alpha. When I'm finding double angles in this kind of question, I usually use the first identity, cosine squared alpha minus sine squared alpha. You can use the other ones if you want. The reason why I choose to use this version is because the denominators end up being the same. So when I subtract the two fractions, I don't have to find a common denominator. And so we can take our values from our triangle. Cosine is going to be 3/5 squared. Sine squared will be 4/5 squared. And that will give me 9/25 minus 16/25, which gives me negative 7/25 for my cosine 2 alpha. Now, I got a negative answer out. And sometimes when we get negative answers, we panic a little bit, right? It's natural. We're like, I don't know, the other one was positive. Did I do something wrong? But look at our pre-thinking. We knew that cosine was going to be negative, and it is negative. All right, our last thing is to find tangent of 2 alpha. Now, if I've already found sine and cosine, I'm going to make this easy for myself and take sine 2 alpha and divide it by cosine 2 alpha. And that's going to give me 24 over 25 divided by negative 7 over 25, which is the same thing as saying 24 over 25 times, times negative 7 over 25. Nope. Oh, 25 over 7, which is super nice because the 25s reduce. And I end up with negative 24 over 7 as my tangent double angle. So let me ask you folks a question here. Is the double angle in quadrant 1 or quadrant 2?
Quadrant 2.
Quadrant 2, you were right. How do you know?
Because it's a negative, not a positive.
Yeah, because the cosine is negative, the tangent is negative, only the sine is positive. So that means that 2 alpha is in quadrant 2. Okay? All right. So are there any questions on this first example right here? Okay. Let's try another one. So example number 2. If tangent of alpha is negative 3 and alpha is in quadrant 2, find the exact values of sine 2 alpha, cosine 2 alpha, and tangent 2 alpha. Then determine the location of 2 alpha. Okay. So let's do some of that same pre-thinking. Alpha is in quadrant 2. That means that alpha is between 90 and 180. What does that mean 2 alpha has to be between?
$180 and $270.
I buy the 180 because double of 90 is 180. But I disagree with the 270.
Okay, so that would be 360.
It'd be 360 because twice of 180 gives you 360, right? If you had an angle that was 179 degrees, if you double it, it's going to be in quadrant 4, right? So we have to open that all the way up to include quadrant 4. Okay. Let's make a similar chart here to look at the signs of sine and cosine. So we know that sine is positive, cosine is positive, tangent is positive in the first quadrant. We know that sine is positive, cosine is negative, and tangent is negative in the second quadrant. What is sine in the third quadrant?
Negative.
It is negative. And cosine?
Negative.
Negative. And tangent?
Positive.
Positive. Good, because the negative divided by a negative gives me a positive. All right, quadrant 4. Sine is going to be negative. Cosine is going to be positive, and that means our tangent will be negative. Okay? So at the end, I'm going to compare the signs of my answer and figure out which quadrant my 2 alpha is in. Now, since I know my triangle or my angle is in quadrant 2, I'm going to draw my triangle as if I were in quadrant 2. And so this is my alpha, okay? If they give me tangent, what 2 sides are they telling me about?
Adjacent and opposite.
Adjacent and opposite, you got it. So -3 is really the same as -3/1, right? So we can say that the opposite side is 3 and the adjacent side is 1. And which one of those gets the negative sign? The 1 or the 3?
The 1.
The 1, exactly, because this is moving in the negative x direction. All right, use your Pythagorean theorem to find that hypotenuse, and then we'll check our numbers and then move on. Okay, so find the length of that hypotenuse. We should get that this hypotenuse is the square root of 10, okay? And because it is not a nice whole number, we will leave it as the square root of 10. Now that we've got our hypotenuse, we can start to fill in our sine 2 alpha, cosine 2 alpha, and tangent 2 alpha, okay? And all we need is our equations from before. So sine 2 alpha is 2 sine alpha cosine alpha, which is 2, 3/√10 times -1/√10. And when we clean this up, it will give us -6/10, or we could say -3/5. Now that makes sense because I know my angle has to be in quadrant 3 or 4, and so sine should be negative for both quadrants. Cosine 2 alpha. Let's use the same one we did last time, cosine squared alpha minus sine squared alpha. And we'll plug in what we have. So -1/√10 squared minus 3/√10 squared. And that gives us 1/10 minus 9/10, which is -8/10 or -4/5. Okay. And then again, as soon as you have sine and cosine, you know you can take your sine divided by your cosine to get your tangent. So -3/5 over -4/5 gives me -3/5 times -5/4, which gives me a positive 3/4. So I found all my double angles. What quadrant is my 2 alpha located in?
The third quadrant,
Third quadrant, and how do you know that?
because the sine and the cosine are both negative, and then the tangent is positive.
Very nice. Okay, so 2 alpha is in quadrant 3, and we can say because sine and cosine are negative and tangent is positive. And that matches with what we did in our pre-thinking. Okay? All right, so not so bad if you have the formulas, which means make sure those formulas get on your cheat sheet. All right, let's take a look at an example where we are going to verify this identity, okay? So your textbook does verifying the identities in a whole separate section, but I like to integrate it into whatever section we're talking about. So we kind of get to see what strategies might work, or like which kinds of identities we need to help prove things. Okay. So we're going to start off with this one. We have cosine of 4 theta equals 8 cosine to the 4 theta minus 8 cosine squared theta plus 1. Okay. And what we're going to do is we're actually going to take this cosine 4 theta and we're going to try and make this simple side way more complicated and try and get it to match the other side. So what I'm going to do here, and again, I know this because we're in the double angle unit, but also I noticed that 4 is an even number. And so I could think of 4 theta as 2 times 2 theta. Okay. So I'm going to make cosine 4 theta into cosine of 2 times 2 theta. And I have that on the other side. Okay. According to the cosine double angle formula, I have 3 different versions. So now let's be very thoughtful about which one we choose. So when I look at the right-hand side, I see a bunch of cosines. I see nothing that has sine on the right-hand side. So let me scroll back up for a moment. If I look at the 3 variations, this one has a sine in it, this one has a sine in it, but this last one has only cosine. I'm going to use the last one for this question because I know that the other side of the equation doesn't have any sines. So why would I pick something that's going to introduce other things I don't want in there? Okay. So everywhere I see a cosine 2u, I'm going to replace it with 2 cosine squared u minus 1. The left-hand side becomes then 2 cosine squared 2 theta minus 1. Okay, so this u is the same as this u. And in our case, our u was 2 theta. So both places where I have the green dot have to be a 2 theta. And I've got my other side. Okay. I'm going to do that one more time because I notice that I have another situation where I have a 2 theta. Okay. So if I have cosine squared, right, I can replace that with, what can I replace that with? Cosine 2 theta is going to be 2 cosine theta, cosine squared theta minus 1, and then I'm going to square it, okay? So cosine 2 theta became this part, and then the square, I square it after, okay? Now I have to FOIL. And so when I know I need to FOIL, I write it out 2 times so that I don't forget to FOIL. I can't tell you how many students, especially on a test, and they're feeling a little nervous and they're like, oh, I'll just square both of those 2 terms and call it a day. That's going to be fine, right? And then they get the question wrong and then they're so sad about it. So we want to avoid that mistake, and we want to make sure we know we need to FOIL. And now we just need to FOIL and distribute. So 2, this becomes 4 cosine to the 4th minus 4 cosine squared plus 1 minus 1 equals the other side. And I think you can probably see it already. If I distribute that 2, I'm going to start to see those 8s that I need on the other side. I get 8 cosine to the 4th theta minus 8 cosine squared theta. And then 2 times 1 is 2, but I have to subtract that 1. So that's where I get that plus 1. And now both sides are equivalent to each other. And so we have verified the identity. Any questions about number 3?
I do.
Okay, what's up?
I don't get how you at first did 2 cosine squared 2 theta minus 1 at the top underneath cosine 2 times 2 theta.
Okay. So you know the identity says cosine of 2u equals 2 cosine squared u minus 1, right?
Yeah.
Okay. So this u is going to go right here. But what we have is cosine of 2 times 2 theta. So u is really this whole thing. So when I replace it on the other side, I need to replace u with 2 theta. And so that's why I have a 2 theta right there.
And then that 2 cosine squared 2 theta minus 1 replaces, like you wouldn't use the cosine 2 times 2 theta instead?
No, I already replaced it.
Okay, okay.
Yeah, I already replaced it, and I don't want to keep it with the 2 times 2 theta because when I look at the other side, everything is just like a 1 theta. It's not 2 thetas.
Okay.
Yeah.
Thank you.
You're welcome. Thank you for asking. I'm sure that was a pretty common question. All right, any other questions about number 3? Okay, let's move on to example 4 then. So I wanted to do one that has to do with a 3 tangent, or a 3 theta, because the last example had a situation where it was an even number, right? We had 4 theta. And so when we saw 4 theta, we were like, well, how can we use the double angle? Because 2 goes into 4 nicely. But 2 does not go into 3 nicely. So we have a different situation here, okay? And so let's take a look at this. I can say that 3 theta is 1 theta plus 2 thetas. So I'm going to take this left-hand side and I'm going to break it up into theta plus 2 theta. And then I want to write the other side, so I'm always thinking like, what am I trying to achieve? And now as soon as I have tangent of theta plus 2 theta, which identity should we be thinking about?
Sum and difference.
Difference, very good. So our tangent sum and difference was tangent u plus tangent v divided by 1 minus tangent u tangent v. Okay. Now, how come I use the one with the tangents and not just sine over cosine?
Because this is a sum and it's not a multiplication.
No, but I could have written it as my sine theta over cosine theta. Like I can always write it like that. But why wouldn't I use that in this case?
Because there's no sine or cosine present.
Yeah, the other side, this side, has no sines and cosines, right? So we want to make sure we move in the direction closer to what we're looking for rather than like further away from what we're looking for. Okay, so that's why in this case, I'm choosing to use the tangent one. All right, so we've made one substitution and we're getting kind of closer. But when we look at the other side, another thing I notice is there's only tangent theta. There's no like two thetas. So I got to get rid of those two thetas somehow. So everywhere I see a tangent to theta, let's go ahead and use our double angle for tangent. Okay, so everywhere we see tangent to theta, we're going to write 2 tangent theta over 1 minus tangent squared theta. So tangent theta plus 2 tangent theta over 1 minus tangent squared theta over 1 minus tangent theta times 2 tangent theta over 1 minus tangent squared theta equals that other side. Okay. So this is our tangent to theta, this is our tangent to theta. And now what we need to do is find some common denominators, turn things into a single fraction, and then I think we'll be able to meet our goal. All right, common denominator on the top is going to be 1 minus tangent squared. Let me just draw that big fraction line. So I've got 1 minus tangent squared theta. That means I will have tangent theta times 1 minus tangent squared theta plus 2 tan theta. And then on the bottom, common denominator is going to be the same thing, 1 minus tangent squared theta. And I'm going to have 1 minus tangent squared theta minus 2 tangent squared theta. And I want to make that equal to what I had on the right-hand side. Now I can find fractions over fractions to be really messy sometimes. So I'm going to keep the top fraction, and then I'm going to write it as times the reciprocal of the bottom fraction, so that my two fractions are side by side and not on top of each other. And as I do that, I'm also going to distribute as I need, okay? So my first fraction is going to become tangent theta minus tangent cubed theta plus 2 tan theta over 1 minus tan squared theta times the reciprocal of the bottom, so 1 minus tangent squared theta over 1 minus, let's combine those, 3 tangent squared theta. And we want that to equal the right-hand side. Okay, so some things reduce here. These two reduce, which makes it way better already. And so now I can write that left-hand side as a single fraction. So we're going to get 3 tan theta minus tan cubed over 1 minus 3 tan squared equals that right-hand side. All right, we are in our home stretch. The last thing we have to do on the top, let's factor out our greatest common factor, which is tangent. And now we've got the same numerator as the right-hand side. And we've already matched our denominator. And so we have verified this identity. Okay. So a lot of algebra in here. I know that sometimes the algebra gets to be a bit much, but it is a really, really useful skill to have, and practicing all these different things will definitely make your future math classes easier. All right, any questions about number 4? Okay. All right. We are going to actually start to look at this idea of solving equations, okay? So again, we'll do a whole section on solving equations on Monday, but I kind of want to start to get this idea in our heads about how we use the different identities to solve them. All right, so in this equation, I have a sine 2x. And immediately I want to think, oh, there's a double angle formula, and I want us to use the double angle formula. That means instead of sine 2x plus sine x equals 0, I can write it as 2 sine x cosine x plus sine x equals 0. The nice thing about writing it like this is I can take out a greatest common factor. And now, because I have something times something equals 0, I can split this into 2 different equations. I can say that one equation is going to be sine x equals 0, and the other equation will be 2 cosine x plus 1 equals 0. Okay, this is going to be a common theme as we solve equations, that we're looking to get common factors out. We're looking to use the identities so that we can get these common factors, and then ultimately we're going to be setting them equal to 0. All right, so Using your unit circle, tell me all the values in your unit circle where sine of an angle equals 0.
Zero and pi.
0 and pi, very nice. Okay, well now we have to do a little bit of work before we answer the second part. So we have to move that 1 to the other side and we have to divide by 2. So really we're looking for cosine x equals -1/2. And so now I want you to use your unit circle to tell me all the angles that have a cosine of -1/2.
120 and 240.
Radians only, please.
2 pi over 3 and 4 pi over 3.
Beautiful, thank you. Okay, so one quick hint to avoid that is if the question gets asked in radians, you gotta answer in radians too, okay? The other thing is if you plan on continuing to take a few more math courses, we gotta get familiar with the radians. And sometimes we're just like, can't I just continue to use degrees? But like the best way to get used to using them is using them whenever you can, okay? So as you make your cheat sheet, make sure that your unit circle has radian measures too, because I'm gonna be looking primarily for radian measures on the exam. All right, so this was kind of a warm up to like, yes, we can use these identities to prove things, to find angle measures, but we can also use them to solve equations, okay? All right, so let's take a look at the half angle identities. So we'll go through a few of these identities and then we'll see about taking a break before we continue, okay? So just like there are double angle identities, there are also something called half angle identities. Now, these half angle identities are also known as power reducing identities. We will not do a lot of work with these in pre-calc. I wanted to show them to you because you will use these in Calc 2. So if Calc 2 is in your future, save these in your brain somewhere because you're going to use them a lot in Calc 2, okay? We're not going to focus on them quite so much, but we'll instead focus on the half angle formulas, okay, which are a little bit different. So these you'll use in Calc 2, save them somewhere so that you'll have that to refer to. I just wanted to show you one example of what it might look like in a proof, okay? But this is not something that I will ask for on the exam. Instead, I will focus on more on the other identities that we've learned. So when we look at this, it says verify the identity. And when we're looking at that left-hand side, okay, they substituted their sine squared with this half angle or power reducing formula. And then they did the same thing with their cosine squared. They replaced it with the cosine squared power reducing formula or half angle identity.
Should we write down this example if it's not needed for the test?
I'll leave that to you.
Okay.
Figure out what works for you. Okay.
Okay.
All right. So then from here, we are looking this 1/2, and this 1/2 gets pulled out into the front as a constant 1/4. Now that's a really common strategy in Calc 1 and in Calc 2 that we try and get all our constants out to the front just to make our other work a little easier. And then this part they got using FOIL. This allowed us to do a second substitution with a variation of the Pythagorean identity. So we know that 1 minus cosine squared gives us sine squared, and so that's the substitution they made. And then they did the half angle identity one more time so that they could continue to reduce that power, and you end up with a situation where all the powers for the trig functions are just 1. Okay? So again, this is a set of identities you'll use in Calc 2. We will not use them really that much in this class, but I wanted you to see them and know when they're going to come up again.
I have a question. I saw the identity is different. I have the formula is different when I took trig. So I have like the square root of the whole identity, which is 1 minus cosine of x divided by 2.
These ones?
Yeah.
Yeah, because you're talking about different formulas. Those are the half angle formulas. The ones that we just talked about are the power reducing formulas.
Okay, so this is different?
Yes.
Okay.
Okay. I did include another example that you can look at if you'd like to, just to kind of see someone's thinking in terms of a proof. Again, this particular set of identities will not be on the exam, but this kind of thinking might be in terms of like, how do you know what to substitute with? How do you know what to simplify? Okay. So let's stop here. And when we come back from break, we're going to take a look at these half angle formulas, which are exactly what you were just talking about. So we'll get a chance to dive into those a little bit more deeply. And then we'll get started on the inverse functions at the end of class if we have time, and I feel confident that we will. Okay, so it is 12:58 right now. So let's be back in about 10 minutes. We'll be back at 1:08, and I will see you folks then. All right. So these half angle formulas are probably what you more traditionally know as your half angle formulas. And some of you mentioned already that you learned these particular formulas in trig, which would be correct. All right. So we're going to continue to add to the list of things that should be on that cheat sheet. And so here we go. Here are the half angle formulas. Okay. So there's one for sine, one for cosine, and then there's 3 variations for tangent. And again, as we go through the problems, it's going to be nice to figure out, okay, here are all 3 in front of me. How do I know which one to use and which one might be best in one situation, but know that that might not be the same case for other situations, that we have to treat every situation as a unique one so that we can figure out what to use when. So I'll give you maybe another minute to finish copying this down if you need, and then we'll move right on into some examples. All right, is there anyone out there who's still copying these down, or is it okay if I move on?
I'm still copying it, sorry.
Okay, no worries. Just give me a quick thumbs up when you're done, okay?
I am done. I don't know my classmate who is still copying it too.
Okay, thank you. All right. So I'm going to go ahead and scroll down here. If you want to just take a quick picture before we move on so that you have access to it, that's totally fine. Otherwise, we will definitely be rewriting these as we go. All right, so first example. It says if secant theta equals 5/4 and theta is in quadrant 1, find the exact values of sine theta over 2, cosine theta over 2, and tangent theta over 2. So very similar to what we saw before with the double angle, only this time we're looking for half angles. Now, if we know that theta is in quadrant 1, we know that theta is between 0 and 90 degrees. And then we also know that half of theta has to be between 0 and 45 degrees. So in our pre-thinking, we already know that sine is going to be positive, cosine is going to be positive, and tangent is going to be positive. This is especially important for half angles because, as you'll notice here, all the half angle ones have a plus minus in the front. Now, it's not like there's two answers. There's one answer, but you have to choose, is it plus or minus? And so what we've already done is choose that every single answer is going to be positive. But in a different example, we'll see that might not always be the case. Okay, so we're going to start the same way. We're going to draw our triangle. And we'll label our theta. And we know that secant is hypotenuse over adjacent. So this is 5 and this is 4. This is a nice right triangle, so I know that that third side is 3. Now I just need to plug everything into the equations. So sine theta over 2 equals plus the square root of 1 minus or 1 plus? Like, is this a minus sign here or is it going to be a plus sign?
A minus sign.
It's going to be a minus sign, okay? So that's just one of the things I want to point out here is that the sine one has a negative, but the cosine has a positive. So they're very similar, just that one of them has a negative, the other has a positive. So this is going to be 1 minus cosine of theta over 2. And now let's plug in the values that we have from our right triangle. So positive square root of 1 minus 4/5 all over 2, which will give me the square root of, let's see, 1 minus 4/5 is 1/5. And I'm going to divide that by 2, which should give me the square root of 1/10. Okay, we're going to do the same thing for cosine. Positive, because we already decided the half angles in quadrant 1. 1 plus 4/5 over 2.
I have question for the first. How could we find this 4/5 if it is the sine? I think supposed to be 3/5.
In the formula, it's cosine of v.
Cosine, okay.
Yeah. Okay.
Okay.
Yeah, they look similar, but they both use cosine, but one is minus and one is.
All right, I got it.
Okay, good. Okay, so 1 plus 4/5 is 9/5. Divided by 2 is going to give me 9/10, underneath a square root. And you can leave this as square root of 9 over 10, or you can reduce it to 3 over root 10. Either way is fine. Okay? And last but not least, I'm going to take the easy way out. I encourage you to do that as well. If you already found sine and you found cosine, divide them and then be on your merry way. Okay? So I'm going to take my sine of theta over 2 and divide it by my cosine of theta over 2. And that's going to give me 1 over root 10 divided by 3 over root 10, which is the same as 1 over root 10 times root 10 over 3, which will give me 1/3 as my tangent half angle. Okay? So a very similar process to the double angle, except you have to choose the sine. I encourage you to choose the sine in advance so you don't forget. All right, so you have to choose the sine and the formulas are different. But other than that, the process is very similar. Okay? Any questions on example number 1? All right, let's move on to.
All the answers, you don't care if you like rationalize it or anything?
I don't have
that. Okay.
Yeah, and the reason is I think it's important like to know how to rationalize it. But, you know, I'm thinking right now, especially in my Calc 2 class, like we do so much other complicated stuff that at the end, it's not really worth rationalizing the denominator. So, all right,
Thank you.
you're welcome. Okay, so example 2, let's do one with a tangent. All right, so tangent equals 1, and theta is in quadrant 3. So I know that means theta has to be between 180 and 270. What does that mean theta over 2 has to be between?
$90 and $135.
Beautiful. How'd you get that?
The half of the angles, the both angles, 180 is 90 and 270 is 135.
Perfect. Yep. So divide everything by 2. Now that means my half angle is in quadrant 2. That means that sine is positive, cosine is negative, and tangent is negative. So I'm making my decisions in advance what the signs of my answers are going to be. All right, let's draw our triangle in quadrant 3. And here's my theta. I know that tangent is 1. That means the opposite and the adjacent are the same length. Now, given the way the triangle's drawn, this is a -1 and this is a -1. Because I'm going in the negative x direction and in the negative y direction. Now, if we use Pythagorean Theorem to find the hypotenuse, we should find that it is the square root of 2. Okay, let's use our formulas to find our half angles. Sine theta over 2 equals positive square root of 1 minus cosine theta. Cosine theta in this case is
-1 over root 2.
-1 over root 2. Very nice. -1 over root 2. Now, you'll notice that I put parentheses around that. The reason I did that is because I don't want us to miss this sign situation, that a negative is going to make it positive, okay? And so when I combine those, I end up with 1 plus 1 over root 2 over 2, or root 2 plus 1 over root 2 all over 2. And this is going to give me the square root of 2 plus 1 over 2 root 2. And it's okay to leave your answer like that, okay? This is going to be a non-calculator test. So if you give me some sort of decimal, I know you cheated and used a calculator, okay? So don't turn this into a decimal. Leave it as a radical and a fraction. All right, let's find our cosine. Before I even write the formula, I'm going to put a minus sign in front of that whole thing, because I want to remind myself at the end, I need a negative for the cosine. And this time I have 1 plus a negative 1 over root 2. This is going to give me negative root 2 minus 1 over root 2 all over 2. Or we can write this as negative root 2 minus 1 over 2 root 2. All right, so very similar to the sine one, except I have this different sign in the front, slightly different signs on the inside. And then last but not least, we find our tangent half angle. That's going to be our sine half angle divided by our cosine half angle. And so you can leave it, believe it or not, as this negative, a big square root. We've got our sine over the cosine. You could leave it like that, or if you simplify a little bit more, these are going to reduce, and we'll end up with root 2 plus 1 over root 2 minus 1. Okay. Any questions about example number 2? All right, let's move on to the next unit. Okay, so all these half angle things are definitely going to be important to know. Your half angles, your double angles, make sure you have all those different variations written down on that cheat sheet. Okay, so I'm going to stop the share here. I'm going to